What time is it? I'm just kidding, guys. I'm super excited because it's time for another video from the Hutchins School Chemistry Lab. This time we're in topic number 3, electrolysis. Let's introduce it. Let's get it done right now. Last time we were talking about electrochemistry, and we were talking about primary cells which produce electrical energy. They run out of steam, the electrochemical cell reaches equilibrium, and that is the end of the reaction. And I indicated that we could perhaps recharge some of those things, which is probably quite in line with your experience of the world. Now, recharging chemical cells is the business of electrolysis, and only secondary cells can be recharged. So, let's have a look at that. Now, this bit is just a little bit of explanation. Let's have a look at what we've going on here. We have here a battery. Let's assume that the blue is the amount of battery, the energy in the battery, the chemical energy, and so we use that using our torch or whatever we're using, and we run out of battery. Now, if we've got a secondary cell, then we can recharge it and somehow magically get back to here. And in fact, that is our current understanding. We know that we've started off with electrochemistry, we've produced energy using electrochemical energy, and we have used that, and we get to this state, and this charging business here is, as far as we're concerned, a little bit of magic. Well, it turns out it's not magic. Surprise, surprise. It is indeed electrolysis, which is what we're about to study now. So I'm going to step you through a very common system which we encounter on a day-to-day basis, perhaps without realizing, where we get recharging going on, and that is the lead-acid battery that you see in your car. We start off with lead and sulfuric acid. Now, this is sulfuric acid, which is H2SO4, and we've lost one of those H pluses already. So it is busily floating off doing something else, and you'll see what that's doing in just a second. But lead reacts with the hydrogen sulfate ion to produce lead sulfate, one free acid, or H plus, or hydronium, and 2 electrons. And those 2 electrons go on a journey, and they meet up with some lead oxide, and 3 of these acids and another one of these hydrogen sulfates to produce pretty much the same products. Actually, we've got here lead sulfate and lead sulfate. So what happens is we start off with lead and lead oxide and a bit of acid, and we end up with lead sulfate. So when we're flat, when our battery's flat, the only things present are lead sulfate, which is the 2 products. We've got water, we've got acid, and we're probably going to have a little bit of hydrogen sulfate left over. So what we do is we use the lead sulfate, a little bit of acid, and we can pump some electrons into that and get back to lead and hydrogen sulfate. So we have reversed the oxidation reaction that occurred at the anode earlier. So here you see lead sulfate, acid, electrons, and lead and hydrogen sulfate. Same thing down here. At the anode, we get the opposite of the previous cathode reaction, and we see the lead sulfate and the 2 waters producing lead oxide, 3 lots of acid, and some hydrogen sulfate. And that's what we see in the charging of our lead acid battery. And we get back to our starting point, ready to go once more. So the question is, which would you rather go down? These are both roller coasters. And which would you rather push the cart back up? I'm not going to answer that just in a minute, but you get to think about it. If you have to push the cart, which one would you like to push the cart up? And if you got to go down one of them, which would you like to go down? We have quite a few similarities between electrolysis and electrochemistry. Let's look at the similarities. Both have an anode and a cathode. Oxidation continues to occur at the anode, and reduction occurs at the cathode. Since oxidation is loss of electrons and we're producing electrons at the anode, obviously they would flow from their source to where they are consumed, so electrons still flow from anode to cathode. Anions continue to move to the anode because we are still producing an excess positive charge as we take our solid metal and produce cations, and our cations continue to move to the cathode. Now let's look at the differences. Well, electrolysis, what we're looking at now, is not a spontaneous process, unlike electrochemistry. Electrolysis consumes energy. Because it's not spontaneous, it only occurs when we put energy in, so it consumes the energy that we put in. Whereas electrochemistry, if you put two electrochemical half cells together appropriately, then you will produce energy. So in this sense, electrolysis is like pushing something uphill, and electrochemistry is like rolling down a hill. In electrolysis, the net E0 is going to be less than 0, and in electrochemistry, as we know, the net E0 is greater than 0. So we're looking for a negative E0. Now in electrolysis, there's no salt bridge and we only use one electrolyte, as opposed to our more familiar at the moment system, where we have two electrolytes and a salt bridge to maintain the balance between them. Now, the big thing to remember in electrolysis, the anode is positive. So it's no longer our cathode that's positive, it's our anode that's positive. Okay, looking at a cell picture, which is what this is, the cells look a little bit different. So notice we only have one vessel here for electrolysis. You can use two inert electrodes, which we have occurring here. We have one single electrolyte, and our electrons move from the positive anode to the negative cathode, as opposed to what we've seen before. This is a Daniell cell again, where we have a negative anode, electrons moving to the positive cathode. Okay, so back to this question, which would you rather go down and which would you rather push the cart back up? Hopefully you're like me and you would much prefer to ride a very exciting roller coaster all the way down. And so this guy here is our analogy for an electrochemical cell. And if you're like me and you don't like pushing heavy carts up steep hills, you would probably choose to push the cart up the very shallow hill that we have here. And this is like an electrochemical cell. Let's revisit some universal facts that are always true. Metals cannot be negative. Fact. That's not particularly pertinent to what we're doing, but it is a universal fact. The other universal fact is that the universe always tends toward the lowest energy. So if the universe has to do the pushing, then it would choose to push the least. It prefers to release the most energy. This is our very large roller coaster where we have electrochemistry. We're releasing the most energy, and it wants to spend the least energy. If you gave an electrolytic cell lots more energy than it needs, it would just do the reaction more rather than choosing to do a harder reaction less. So the universe always tends towards the lowest energy. Fact. So let's look at our Daniell cell. Last time we had copper and we had zinc, so copper 2 reacting with zinc. And what we know is that we like a nice negative gradient between reacting species. My oxidizer is above and to the left of my reducer, looking for this negative gradient. In electrolysis, we're looking for the opposite. So in electrolysis, what we would see is a reaction between zinc 2 and copper, because as we looked at when we were reversing the reaction of the lead acid battery, instead of going from here to here, we're going now from here to here and from here to here. So we're reversing the reaction. When we do that, we're looking for a shallow gradient. So if we're in a competing reaction type situation, what we'd prefer to see is something a little bit more like this. Electrolysis would really like a shallower gradient. It seeks the easiest path, so the smallest difference in potential looks for the most shallow path, whereas electrochemistry looks for the most steep path in a negative gradient. So we're looking for electrochemistry going this way, electrolysis shallow and back the other way. Electrolysis has many applications. They include electroplating a piece of metal, so perhaps electroplating a precious metal on top of a not so precious metal. You can use electrolysis to extract reactive metals such as aluminium, sodium, potassium, calcium and magnesium. You can use electrolysis to produce pure gases like chlorine, hydrogen, oxygen, sodium hydroxide, which is not a gas, and fluorine. And you can anodize aluminium, which is a protective process that we'll go into in the corrosion unit. You can use it to recharge batteries, which is how we got here in the first place, and you can use it to purify metal. So extraction of reactive metals and purification of metals. So that's it for today, and looking forward to seeing you in the next video.